Very good evening, Lakshmi. No, no, no. Still 2 to 3 session more left. Okay, that is some miscellaneous section left, and then the complete chapter name is what? Ether, right? Okay. Like, why are you saying sorry? Very good evening, sir. So let's just wait for some time, okay? Let's wait for 1 minute more, okay? Not more than that, and then we are going to start with the class. Okay, so let's start with the class. Okay, so let me just give you a quick brief. First of all, very good evening, everyone, and this is going to be the seventh session. Okay, so let me just check what is the session number. So seventh. Okay, so let's continue now. Okay, so in the previous class, if you remember, we discussed about the semi-Pinna reaction there. Okay, the last topic that is we discussed about that the semi-Pinna. Wait. Okay, semi-Pinna colon reaction is there. So then there we discuss about that in place of the diol, actually we are having some other Z group there, and this is how that we are getting normally, that is a ketone there. Okay, so this is how the simple thing we discuss. Now let's start with the today's class. So in today's class, what we are going to discuss the reaction of phenol. So that's it. This is all for the alcohol. Now we're going to discuss about the phenol part there. Okay, so in the reaction of the phenol, the topic which we are going to cover in today's class is the electrophilic substitution reaction, and then kolbes reaction, and then Riemann-Tiemann reaction, and then the reaction with zinc dust, and then oxidation reaction. The last one is the reaction with FeCl. Okay, so these are the things we are going to discuss one by one. So let's just start with the very first, that is electrophilic substitution reaction. Okay, so when we are using this word electrophilic substitution reaction, I guess we already covered this topic so many times. Okay, that electrophilic substitution reaction. So what is the meaning of this? That is electrophilic substitution reaction means that some electrophile is going to substitute. For example, since this is a reaction of the phenol, so definitely we are going to use the phenol part here. So for example, this is my phenol. Any electrophilic substitution reaction anyone wants to try? Oh, I'm sorry, wait. Yes, any kind of electrophilic substitution reaction, we already covered this topic in the previous class as well, haloalkane and halurine, if you remember. Yes, please, any reaction, do you know? Very good evening, Batula. I guess I know you, right? Anyway, please answer the question. Yes, very good. Hallucination, nitration, sulfonation, Friedel-Crafts alkylation. This one, okay? Okay, sodium phenoxide. Okay, like this is the first part, but you are right, Shiva. Okay, so let's just start with this. Like what we are going to discuss now. And nitration is also there. Yes, yes. So many reactions there, right? So it means the point is clear, but we are going to do this. And in the phenol part, basically we are going to discuss about two things. That is hallucination, okay? Hallucination and especially the bromine one. Because obviously we are going to cover only that topic which is important for us. So hallucination or the nitration part here. Okay, hallucination or nitration. So first of all, as everyone know, this is a plus M group, right? If this is a plus M group, so definitely that the incoming electrophile combine at ortho or para position. Maybe ortho can be there or maybe para can be there. So let's just talk about if in the same reaction I am using this HNO2, okay, and like what we're getting there, this is a OH. Maybe that is the at para NO2 group connected, or maybe that at ortho position the NO2 group connected. Okay, so wait. And here we are talking about what is the name for this reaction? It's a nitration there. Now, so first of all, between para and ortho, let me just write it's a para or it's a ortho. So according to you, which one is more stable? We are going to discuss about concentration part, any part there, okay? Very good evening, Arul. How are you, Arul? First, answer this question. So para is the major one or the like ortho is the major one? Wait. I have to change. This is HNO3, okay? First, just answer the question. Para. Para, okay. But you know, there is a plus point. Focus. There is a something. Maybe that changed the answer. What is it? It's a ortho nitro phenol. So which one is most stable according to you? Ortho definitely, right? Why? Because there are intramolecular hydrogen bonding is present, okay? So yes, of course. We discussed this thing so many time, okay? I don't know. Same. I'm never ever checking my dashboard. Okay, I will check and then let you know. Okay, but Ula, I'm sorry about this. I don't know about this. Okay. So, like in this case, yes, we are assuming every time that para is going to be the stable one because the plus point is what? Okay, that both are anti to one another. But in this case, there is a one more point. It's a orthonitrophenol, and we discussed already this point earlier. It's steam volatile, right? We covered this topic, although I will going to explain this point as well again. So this is a NO and it's a NO2 there. Okay then. So look at this. This is how that is intramolecular hydrogen bonding is present. So just for this part only, this is going to be the stable product. Okay, ortho one. So intramolecular hydrogen bonding. Okay, intramolecular hydrogen bonding. That's it. Okay, now next question. Do you know, in this case, we are going to use the diluted HNO3, not the concentrated one. And for this one, you will tell me the answer. Why not concentrated? You know, every time for the nitration, we're using diluted HNO3 and even H2SO4 as well. Yes, please, anyone? Okay. So let me just give you a kind of hint and then you are able to answer the question. This is my question, okay? Just try to answer the question. For example, if let's suppose I'm having a plain benzene, okay? It means normal benzene. And the second case, that is a OH there. Okay, so what is the nitration reason there? That is HNO3. And which HNO3? That concentrated HNO3. And what we are using as well? H2SO4 as well, you know? H2SO4, what is the function of the H2SO4? If you remember, this is behaving like a catalyst. It increase the rate of reaction. So it's basically being like a catalyst here. Okay then. So now in this case, but on the other hand, in this case, we are using only diluted HNO3, not even we are using H2SO4. So then question be like, why? Why not in phenol we are using concentrated HNO3? So what will be the reason behind this? Oxidizing nature. It won't. No, I know the product meaning. Okay, I'm not asking this. My question to you, why not concentrated? You know, like you already answered the question, although that picric acid. But why? What is the reason behind? Have you ever thought about this? Like why concentrated give the picric acid, not the diluted one? No. Okay. So try to understand my point. Okay. So just let me know. This is simple benzene. Okay. In the second case, it's a phenol there. Okay. Now some electrophile is waiting. So can you just tell me where the electrophile is going to attack first? Is it benzene or is it phenol? And then this question, maybe Poor yield. Okay, Shiva, not an issue, but just try to answer the question. Which in on benzene or on phenol, like A or B, where the electrophile is going to attack first? And this is the answer for the given question. Yes? Anyone? Electrophile deficient, so where it is going to attack, where we are having a more electron, you can say electron density, right? So see this B obviously. So in this case, what is happening there? Look at this side, we are having OH be like, I'm a plus M group, so I'm going to increase the electron density. So now that HNO be like, okay, so look at this. If we are using HNO3 there, so benzene will like, I'm not going to do the reaction because I'm a benzene. Benzene technically never ever undergo these kind of reaction normally at normal condition. So then, and this be like that, okay, benzene be like, I want HNO3. Which HNO3? Concentrated HNO3. And obviously, plus we're using H2SO4 as well. But this be like, I'm already electron rich. Okay, not an issue. I can take the electrophile easily. So that's why in this case, you can simply use normal diluted HNO3. Okay, so why? Because this is automatically eager for the reaction. It's not like the benzene. Okay, second point, that as we discussed in the 11th class already, it's a very good catalyst. So this will like not an issue. I can react with the diluted, not even require the H2SO4. And if let's suppose you be like, no, we are going to use the concentrated HNO3. So this phenol be like, okay, I am very, very electron rich molecule, you can say. Okay, so if in place of diluted one, if you're using concentrated one, so what we are end up there, that at every position, it's a ortho and para directing. So what is happening there, that with respect to this OH, that NO2 group connected here, NO2 group connected here, and even NO2 group connected here. So what is the simple reason, that phenol is automatically electron rich, so hence it's not required that much harsh condition for the reaction if you are using concentrated one. So this is enough electron rich so that it can combine so that it can combine NO2 group at all the position. Okay, so this is one of the famous question. Why when we're using concentrated HNO3 we are end up with the picric acid? Okay, I hope the question is clear for everyone, or the concept is clear for everyone. Okay, so this is the simple logic. Okay, so you can say in this case, if we are using diluted one, we are getting ortho and para, and which one is the major one? This is my major. Okay, so wait, I will change the position of my video just for a while. It's a major product. Okay, so if it is a major product means, now the question will be like, why this is a major product? Because the answer is very simple: intramolecular hydrogen bonding. But in the same phenol, if let's suppose I am using concentrated HNO3, so we are end up with this thing, and what is it? It's nothing. It's a picric acid. Okay, it's a picric acid. And do you know, it's a yellow color even. Okay, like very intense yellow color. How the question frame from this topic, there's a some compound A, when you to add concentrated HNO3 we are getting an intense yellow color. So the question wants to highlight to you that picric acid is the thing which we are getting there. It's a yellow color thing. Okay, and anyone, can you just tell me the IUPAC name for this, for picric acid? Picric is the common name. Yes, please. What is the IUPAC name for this OH and NO, this part? Yes, very good, Many. Okay, so the answer is very simple. Very good, Niharika, and 135 nitrophenol. No, 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 no. If you have to compare between OH and NO2 group, okay, priority wise, OH got the first priority, Shiva. Okay, for this one, you have to check the priority table, that OH and NO2 is not even a functional group. It is just simply behaving like a substituent. Okay, so that's why the numbering started from OH, okay, not from the NO2 part. For this one, you have to check it for the priority table if you don't know. Okay, so let's see the numbering. So in this case, that 1, 2, 3, 4, 5, 6. Okay, so what is the name for this compound? The name for this compound is what? At second position you are having nitro, and at fourth position or at sixth position, so 243 trinitro. Okay, 243 trinitrophenol, and hence this is the IUPAC name for this one. Okay, So any issue with the topic, any point not clear? Okay, let me just quickly brief that in phenol we're using dilute HNO3, so we're end up with para or ortho with mono substitution. But if we are using concentrated HNO3, that for this case we're getting that picric acid. It's really, 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 really important concept. Okay, now next topic, as we already covered, like we are going to discuss about only the two portion here, halogenation and nitration part. So nitration part is done. Let me just erase this, okay? So nitration part is done. Now let's just talk about the halogenation. And in halogenation, the important topic of discussion is going to be the bromination. Okay, so let's just talk about the bromination. Okay then, cool. So in this case, okay, have you ever heard about bromine water test? Maybe you already know. That is a bromine water test. Let me know. Sorry. First of all, answer this. What is bromine water test? And the second thing, that is in the bromine water test, really we are going to use the water. Two question for you, okay? Answer this question. To find unsaturation, very good. To test unsaturation. So now answer this question, please. Benzene, give this test positive or not? If I'm having benzene, so should I go with the bromine water test or not? No, right. Okay. So next thing is what? Seriously, in this case, we are using that water or any solvent we are using. You know, the name of the test is bromine. So something is maybe connected with the water or not. You're using water here. But in my memory, I guess in our school time, we are going to use any organic solvent, not water. You know, it's an explosive, yes, ma'am, and bromine added to unsaturated compound, color change observed. Now, my question to you, in bromine water test, which we are using for checking the unsaturation, should I to use water or not? This is my question. Okay, wait. So basically, what is the bromine water test? Look at this. You're having some carbon-carbon double bond, right? And then you're using some kind of bromine simply. Okay. And then what is happening there? That at both the position, it's an anti-attack. One bromine connected here, one bromine connected here. So basically, it's a brown in color, right? So before the reaction, it's a brown in color. Maybe you already know the color of the bromine, so it's a brown color there, like orange is brownish color. Okay, and now that obviously we break the bromine, so it's a colorless solution. So like what is the color change? The brown there is a colorless or sometimes not very good color, like not clear solution, but little bit change in a color there. So that is a colorless, you can say. Okay, simply this is the concept here. Just try to observe the thing. What if I'm using bromine and water? Okay, both. So what is happening? You know that this is bromine and this is water, right? So what is water? One is H positive and one is OH negative ion. Simple this. So do you know what is happening? That if you are using a bromine with a polar solvent, okay? If you are using bromine with a polar solvent, so what is going to happen in this case? That one bromine combined with OH part, okay, and OKHB is simply released there. So what is the problem with the reaction now? See the problem with the reaction, that now in this case, instead of this, like both the bromine is going to connect, what is really going to connect now, that if you're having a carbon carbon double bond, so maybe at one position bromine connected and maybe one position OH connected. So the problem is what, that our solution is not working properly now. So that's why in the lab, if you want to go with the bromine water test, we are going to use a non-polar solvent. So what is the, like, not complete non-polar, which is the main solvent we are using for this one, like the famous one CCl4, okay, tetrachlorocarbon. Or the next one is what, CHCl3, or even you can use C2Cl2 there. Okay, so means what I want to explain from this test simply to you, that if you were to use the bromine with different kind of thing, Okay, one thing make this point very clear. If you're using bromine with the water, so the reaction is little bit vigorous. Okay. No, actually, we have to go with the non-polar solvent. Maximum in the laboratory, maybe you never ever form the bromine water because you know the bromine is highly, highly dangerous. Okay, if let's suppose accidentally if there's a one drop fall on your hand, so that there's a hole created on your hand. Okay, it's even highly explosive as compared to the H2SO4. Okay, so that's why we are going to award you have, okay? Then you're lucky because you know in our college time even they are not allowing us just to form the bromine water. So but okay, if you do, so most of the time we are avoiding the water. Water we are not using in this reaction. Okay, the CCl4 is the common reagent or the CH2Cl2 there. Okay. Okay, Shiva. So what is the point I want to explain to you that if you're using bromine with the water, so the reaction is different. Okay, so be noted, bromine reaction with water is little bit explosive kind of thing. Okay, so why I'm highlighting this thing, bromine water? What is the meaning of bromine water? Because see, we are going to discuss about now bromination, and same like the concentrated and that diluted one, we are getting a different product for the bromination. But let me just first finish like what is the bromination or actually what we are going to do there, okay? So in this case, first of all, let's talk about the bromine. Okay, so simple, this is a bromine. So we have to classify the bromine test into the two part on the basis of the solvent there. So we are using different kind of solvent as we discussed that one is the water. So it's a bromine water like bromine plus water. We are using any kind of bromine plus water and on the other hand side you can use any CS2. Okay, now please answer this. Is it polar or non-polar? Okay, first answer this question. Or you can use CHCl3 as well. Okay, I know it's a polar but not very polar, you know, little bit polarity there. So yes, please. Or let me just write in a bracket that is a less polar or like non-polar kind of solvent. Less polar or non-polar solvent. And on the other hand, this side we're using a polar solvent. Yes, please. Although I already highlighted CS2 is a non-polar, right? So CS2 is a non-polar. Why CS2 is a non-polar? Okay, highly polar. So let's discuss about the bromination now. Okay, so let me just write on a single point, single slide only, so that you are able to understand my point. Okay then, so if let's suppose this is a benzene and it's a phenol. So in the first case, if you're using bromine, and yes, it's really important topic again like the HNO3. If I'm using H2SO4 or that is a CHCl3 or CCl4 there. So in this case, that same thing, ortho and para directing. Okay, again it's a ortho and para directing there. So what we're getting simply that maybe at ortho position or maybe at para position, the bromine is going to connect. And this time, same question, para is major or ortho is major. Okay, so it's a ortho product or plus which it's a para product. So which one is more stable now? Para. Okay, this time there is a no issue like because no hydrogen bonding kind of thing exists. Okay, so it's a normally the major product simply. Oh, sorry. It's a major one and it's a minor one. But in the same reaction, if I'm using bromine water, okay, because you know the problem with the student, why I'm explaining the water and all this analogy, because we used to think if we are adding water, so it means we are decreasing the power of a bromine. Okay, like diluted and concentrated one. So that's why be noted with the bromine, if you're using water, then the reaction have to be vigorous. Okay, so like in this case, what we are getting that if this is a OH, so bromine may be connected here or here or here. So this is how the difference. Okay, this is all for the bromination. There is a so many reaction is going to happen like chlorination you can go, but important is what these two reaction. One is bromination, one is nitration. Okay, then this is all for the like electrophilic reactions there. So now let me just check some questions if we are having. Okay, so first answer this question. Okay, It's easy question. Answer the question. Question be like phenol when first reacted with the concentrated okay acid with okay wait. For this question, I am sorry for this. I missed a concept for you. Okay, let's just wait. Okay, I will explain this. What is this written in a statement? So there is a method of preparation for picric acid. If you want to form a picric acid, okay, like one method we discussed already. Wait, that is the one method we already covered. If you are having a phenol, okay, and if you're using concentrated HNO3, so in this case, that is this is the first method by which we're getting a picric acid, OH or NO2 or NO2 or NO2. So this is normally a picric acid, but so it's a picric acid. This is a first method, or you can follow the second method as well. That in this case, what is the step? First of all, you have to go with the phenol. Okay, again, this is a phenol, and the second step is going to be the sulfonation, concentrated H2SO4, and then you can go with the sulfonation. So in this case, that SO3H, okay, I hope this point is clear why the SO3H connected at more than one position, because again phenol is more electron rich. We're using concentrated H2SO4, so that's why as compared to the one place it combined with the two place there. Okay, now in this case, if I'm using again that is concentrated HNO3, so what we are getting? Same picric acid. Okay, so this is a method number two. Now, if you have to compare between a method number one and method number two, so this is the best method. Okay, this is the best method for the preparation of picric acid. First, go with the sulfonation and then go with the concentrated HNO3. Okay, so in this case, the yield is poor. Although we are just like okay using this reaction, but in this case, the yield is poor, not very good yield. But on the other hand, just because of the presence of SO3 now, the reaction rate little bit increase, and in this case the yield of the product is very good there. Okay, so there's a two method good yield. Okay, now let's solve the question. Okay, after this, now the statement part will be clear for you. So now read this. Phenol, when it is react first with the concentrated sulfuric acid and then with concentrated HNO3, so what we are getting? So you know the question want to highlight this statement to you, that the sulfuric acid and then HNO3. Okay, so yes, answer the question please. Easy, right? B. Okay, very good everyone. So that's it. This is all for the question. Now next question. It's interesting question. So answer this question. First, this is a question. On the next slide, we are having options. It's an advanced question. So just first analyze the question and then we are moving toward the next slide. Okay, so read this. So what does the question want to say? That you are given with some this kind of that structure there. And in this structure, that first of all I'm using X as a iodine. So you have to decide that iodine is going to combine at all the three position like this. First point. The second one is what? If you're using the bromine, so same that all three position occupied with the bromine, or the third one is what? That is a chlorine. So same question is there. Like iodine go with one place, two place, three place. So how to like decide the product? Okay, this is a question. Analyze this 1 minute for you, not 1 minute, not 30 second. Okay, read this carefully, and then we'll move to the option so that you will get the point like how to approach the question. Okay, are you done now? Please confirm if you are done with the question. Okay, I hope it's done now. So let's go with the options. So these are the options. Okay, So what is the reason? Like steric effect of halogen we have to consider, steric effect of the tertiary butyl we have to consider, or the electronic effect of phenolic group we have to consider, or the electronic effect of tertiary group we are going to consider. Like what more than one option can be correct as well, okay? So it's a MSQ type question. So now answer the question, please. Take your time, okay? And then answer the question properly. ABC, okay, Mini. So you already know the answer, or you just solve this? B and D, okay. Okay, and B. Okay, B and D. C as well. Okay, solved it. A, B, C. No, actually, I just thought C already solved. That's why I'm asking. It's not like A and B and C is the correct answer, Batula. Okay, so let's try to understand the question. Okay, so means like partially you're right, steric effect of halogen or like tertiary butyl group or the electronic effect. Or like let's assume maybe D is also the option there, DD. Okay, so you can say that first of all, it this can be the answer as well. Okay, now let's back to other question. What we are having a normal phenol and there's some group connected at meta position. Okay, and you will answer the question. For example, if this is a phenol, right? And this is my OH group, and this is some CCH3. Okay, now first answer this question. Some halogen is waiting. In short, some electrophile is waiting, right? And so this is a plus M group and this is a plus H group. Okay, so right now plus H is not going to work. Why? Because there is a no alpha hydrogen is present. Okay, I hope you know that with respect to this benzene, this carbon has zero alpha hydrogen. So hence hyperconjugation effect is not going to work in this case. Okay, so although carbon plus H we are going to assume, but still in this case plus I is there. Okay, so now according to this one, as you know, like plus am or the plus h or a plus I, so it is a ortho and para directing, and this is also the ortho and para directing. So which one is going to decide the thing? Like according to the OH, this position is visible, this position is visible, or this position is visible. Okay, and according to the this group, this position is visible or this position is visible or this position is also visible, then who's going to be the deciding factor here? Is it OH or is it CHCH sorry, CCH3 thrice is there? Okay, Dashika, right now my question to you, that there is a some halogen. Okay, halogen is electrophile. So now both are the ammo or a plus, and you can say both are the electron donating group. So if you know there is a more than one substituent is present, then who's going to decide the incoming thing? Okay, maybe you already know, right? CH3 there. No, listen my point. Okay, maybe you don't know the concept. So listen my point. That let's discuss three concept. Okay, so in the first one, this is OH group. Okay, and let's suppose there is a OCH3 group. Okay, condition number two. There is a OH group or there is a NO2 group. Okay, condition number three, that this is a NO2 group, or let's say this is a mm, okay, COH group. Okay, so in this case, what is the point? So look at this. This is electron donating group, and this is electron donating group. Okay, so you can say in short, it's a activating group. It's a activating group because it's provide electron density to the benzene. It means increase electron density on a benzene. Okay, and same here, this is also the electron donating group. Okay, let me just mark both are the electron donating or both are the activating group. The case number one, you can say. The case number two, that is this is electron donating group and this is electron withdrawing group. Okay, and in this case both are the electron withdrawing group. Okay, now let's discuss about this. For example, if some electrophile is waiting, electrophile be like, I want to attack. So OH be like, I'm donating. OCS be like, I'm also donating. So then they start fighting. So who's going to win? Obviously the stronger one. And now you will tell me between OH and OCS3, which one has a maximum plus M effect? Yes, please. Which one has a maximum plus M effect? Is it OH group or is it OCS3 group? Yes, please. Who's the stronger one? Which one is the stronger activating group here? OH, very good, Niharika. So OH is the strong electron donating group there, okay? So you can say in this case, who's the deciding factor? The OH is the deciding factor. Okay? The condition number one, if both are activating. The condition number two, that if both one is activating, one is deactivating. So the fight not an issue. So OH will like, I'm the winner, I'm going to decide because I'm the electron donating one. And this is for electrophilic substitution reaction because why? It's a scepter. Okay, just don't apply this concept for the nucleophilic reaction. Okay, be noted everyone, it's important. Now between this and this, then who's going to decide again? That stronger one. So means what is the simple story? If two donating one, stronger one is the deciding factor. If both are the withdrawing one, stronger one is the deciding. But if one is electron donating, one is donating withdrawing one, so donation is the deciding factor. First point clear? Now that if we are having three effect like mesomeric or the hyperconjugation or the inductive effect, we discussed this thing so many times that mesomeric is the more dominating or the hyperconjugation is more dominating or the inductive effect. Yes or no? We know this. Now let's just back again to the question where we're discussing the thing. See, this is OH. It's a plus M. See, I already give you a kind of hint there. It's a plus M group. Or even the OH has a lone pair. And on other hand, this is a plus I. So you know, Lakshmi, plus I is not very the stronger one, right? So then who's going to decide? Which is going to decide the thing. So in this question, which electronic effect is really participating? Who's going to decide the incoming group? Definitely OH. Not this butyl group. Not this tertiary butyl group. Okay, so I hope this point is clear. First of all, how to decide. And Dishika, please let me know, is this point clear? Plus M, right? Dashika, are you getting now how to decide? Like where who's going to decide the electrophile is going to connect where or there? Although in this case there's a tie like all ortho meta and para is same, but still because we want to select the option. Now let's back again. Read the option number one. The steric effect of halogen. Okay, hold on for this. Look at this. The steric effect of the tertiary butyl group. Okay, electronic effect of the phenolic group or electronic effect of the tertiary butyl group. Now between C and D, right now, just by using the first concept only, according to you, which one is the correct answer here? Like C or D? Yes, please, quickly answer the question. Because you know, most of you give D is the correct answer. So between C and D, who's going to decide which electronic effect we are going to follow here? Obviously the OH. You know, oxygen has a lone pair, carbon don't have any kind of lone pair, right? So between C and D, that obviously C is going to be the correct answer, right? It means D is not the correct here. Okay, so you know these two statements are, you can say, opposite to one another, so it's incorrect. Now let's decide between A or B there. Okay, so now let's just back here. Okay, I'm erasing this now. Okay, so now between three condition, let me just write the numbering so that you can get my point. Let's suppose this is a position number one, this is a position number two, and this is a position number three. According to you, which one is the suitable position for the attack of the electrophile? This, okay? Look at this. It's a carbon, okay? One carbon, two carbon, three carbon. So, in this case, if you have to observe this part only, so it's a tertiary butyl. Are you done now? It's a tertiary butyl, okay? Dashika, that three carbon and connected with three more carbon there. Okay, tertiary. It's a tertiary butyl. Okay, I'm assuming you're done. Okay then. Yes, please answer the question. Which position is more feasible according to you for the electrophile? Is it one, two, or three? The right now the question going on based on the GOC. The rule, simple rule, that three consecutive group is never ever stable. Three consecutive group is never ever stable. Right? So let's just observe this point here, that in this case, if let's suppose I have to connect a group here. Okay, let's suppose some Z group is there like this. I'm erasing this, okay? So look at this. Three group is there. So look at this. That is the 1OH or the Z or the tertiary butyl. How much hindrance is there. So it means this position is not feasible. This position is not feasible for what? We are having three things. The question asks what? Let me just back again. That you can use iodine, you can use bromine, or you can use chlorine. So means between chlorine, iodine, and bromine. So let me just write if X is my chlorine, or let's see this G. Okay, not use X. This G red one. Z can be iodine, Z can be chlorine, or Z can be bromine. So the problem is about three things, and G is fitting. Like you try to fit the Z between OH and this bulky group there. So now my question to you, between iodine, chlorine, and bromine, if you want to insist, which one you are going to insist? Is it chlorine, bromine, or iodine? Definitely, I go with the chlorine. Right? So at this position, the position number one is blocked by the two thing. Okay, so what is the position number one? Position number one is not feasible for iodine or not for bromine. Only chlorine is possible. Okay, so let me just write that is this first position. Only chlorine is okay. First point. And what is the reason behind this? That hindrance, the steric effect, the hindrance of this bulky group there. Hindrance. Bulky group, hindrance is there. Okay then. So let's just back here. The first option number one, sorry B, that is the steric effect of the tertiary butyl group going to affect the product? Definitely yes. So it's correct answer. Steric effect, the halogen is going to affect the product? Yes. I just cross. If I'm having iodine or chlorine or bromine, iodine and bromine is not going to fit because they're having an issue with the size. Okay, although I hope now the question is clear that answer for this question is the option number A, and option number B, and option number C. But let me just finish the question again. So means what we are discussing, one position is not feasible for iodine, chlorine, and bromine. Okay, only for feasible for the chlorine. Okay. Now let's back here again. Now for the position number two. For the position number two, who's going to participate here? Again, think about it. This is a bulky group, but not three consecutive group. I'm repeating my statement one more time. Listen my point. At position number two, that right now these three group is not consecutive. Okay, three group is not consecutive. So at second position, for the second position, which one is the suitable thing? That iodine be like, no, iodine be like, I can't go because it's a bulky group. So iodine, there is a again no. So for the position number two, iodine there, no. Bromine there, bromine be like, I can adjust. Okay, okay. Chlorine there, yes, chlorine is also there. So means at position number two, two group can be combined there. Okay now. Then how about the like the last third one? The third one is the most visible place. Which is a teeny tiny thing, not bulky there. So at third position, who is going to affect there, or who is going to connect simply? That is, you can say at third position iodine, yes. Bromine, yes. Or chlorine, yes. Okay, all three there is a yes. So one position only chlorine, second position bromine and chlorine, third position iodine, bromine and chlorine. Now let me just quickly brief what I want to explain to you. Question said, if you are having a phenol, okay, just try to understand. If you are having a phenol, and this is C and CH3 group is there. First of all, you have to go with the iodination. First of all, I2 if you are using. So only one thing we are getting, that only at this position iodine group is connected. Okay, so what is it? It's a mono. It's a mono hallucinated, right? Why mono? Because at only one position the iodine is connected here. Mono hallucinated, you can say. Okay, if I'm using chlorine there, so what is happening there? If I'm using chlorine, so chlorine can be combined at all three position. Okay, if this is a OH, chlorine can be connected here, chlorine can be connected here, or chlorine can be connected here as well, because chlorine is not large in size. On the other hand, the last one, look at this. If I'm using bromine there, so what is happening for the bromine? If you're using a bromine there, look at this. It's a OH, it's a the CH3 there. And look at this. Now, bromine may be connected here or bromine may be connected here. What is it? It's a trihallucinated, right? And this is a dihallucinated. Okay, and this is given in the question. Okay, the thing which what I just explained to you already given in the question. Let's read the question one more time and try to understand. Question already discuss, already give you the hint. If X is what, iodine, so monohallucinated you are getting. If bromine, dihallucinated. If chlorine, so trihallucinated. So question simply want to ask to you now that why we are getting three different product with different hallucin. So what is the reason? The first reason, the OH electronic effect. Second reason, the bulky group, the you can say that is the bulkiness of this group. Second reason. Third reason, that the bulkiness of the iodine or chlorine bromine, you can say hallucin there. So three reason. First, OH group plus M effect. Second, tertiary butyl bulkiness. Third reason, bulkiness of hallucin there. And hence the answer for this question is what? uh, A, B, and C is the correct here. Okay, any problem with the question still not clear, please let me know. Okay, I will explain. Wait for a while. Steric effect. Okay. You know the meaning of steric effect, Diksha? That bulky. You know the crowd bulkiness is there. Think about it. Okay. Let's suppose um, this is a OH. Okay. This is a OH. This. Okay. And this group be like this. You know, three carbon is there. So you know steric. Steric means space, space. So they are dissipate a space around it. You know, steric means space, space, space related. Okay, and this is wedge. Let's suppose if I have to fit the iodine there, okay? This is iodine. So look at this. This is a space of the iodine. W is the space for the iodine, like this. Okay, and iodine is larger in size. So look at this, what is happening. Noting something? That iodine has a space. There's a some electron cloud moving in a iodine. You know how much large is the iodine? Obviously the size wise maximum size, okay, in between chlorine, bromine, and iodine or fluorine in this. And look at this, what is it? It's a space of this, what, that the tertiary butyl group. So space, both space combine, overlap, and it means when two things start overlapping, repulsion start. You know, electron cloud be like we are revolving. Okay, and in this case the second electron cloud be like I'm also revolving. You know, electron actually what is happening, they dissipate electron cloud itself. So electron be like come closer and repulsion starts. So what is happening, the space of the two molecule, if they're large to there, come closer, repulsion, and obviously they are not going to be the stable one. So what is steric effect? When the large is sorry, when the size is maximum, there's space overlap, and due to this, the repulsion between electron take place. You know, we use crowd just because of the bulky size. There's a crowd there, but actual reason is what? That electrons start repelling one another. You know, chemistry don't know anything about the crowd, right? I will explain. Just wait for a while, Batula. Okay? Is this point clear? Dashika. Okay. So yes, but Ula, the answer is very simple again. That first of all, that OH is not going to fit the iodine and bromine. So, but still, you know, the crowd. It's not like, see, that is if you're observing this with respect to this is the one carbon. And in this case, there's a second carbon. So the same position, the bulkiness, the crowdiness of this group still maintained there. So maybe the iodine connected here, or maybe the iodine connected there. Both is affected by the bulkiness. But what is the point here? If look at the bromine there, so bromine good like repel there, but bromine is not that much. There is a some space of the bromine this side as well, and there is a something, nothing is present for the repulsion. So for the bromine, the size is small, so the bulkiness of this group is not enough so that we omit the bromine. But iodine still has a large size. The bulkiness of the CeCH3 is still going to affect the iodine. Hence, at second position, iodine attack still not visible. The answer is very simple: the issue of the size. Okay, Batula. So that's why the second position not visible for the iodine. Okay, so I guess done, right? Okay, so let's continue, right? So this is all for the reaction. What is the name of the reaction? Electrophilic substitution reaction, right? So now let's start with the next reaction. That is back again. So first part is done. Although my target is to complete all the reaction, but I guess it's not possible right now. So let's start with the second one. That is a kolbes reaction. Kolbes reaction. Have you ever heard about this kolbes somewhere? Kolbes reaction. Something strike in your mind? Okay, if you don't know, listen my point. This is not Kolbe's electrolysis. This is a Kolbe's reaction only, okay? There's a difference between Kolbe's electrolysis and this point here. Okay? Why I'm asking the question? Just make this point very clear, okay? I'm like you. Sorry, Siddhi, I'm not getting your point. No, 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 I'm not like that. Okay, actually, I'm okay. The student which are joining here, okay, those are my regular student. Okay, so we are just finishing the syllabus here. Okay, I'm not making any random video on any random topic. Okay, we are just left with the 12th topic. Okay, so the we are just completing the syllabus here only. Okay, so Sidhu, you're not from the 12th class. So like we already covered in our regular classes, we already wrap up the metallurgy. So after that, we are discussing here like haloalkane, halourine chapter, and then alkyl phenol ether, then carboxylic acid, then amine, and then the biochemistry only. Okay, I hope it's clear now, right? I know Kabil Ame. Okay, sorry, I don't know about this what you are writing here. Okay, so this is all for the Kalbe's reaction there. Okay, Kalbe's reaction. So let's start actually what is Kalbe's reaction. So like first of all, make this point very clear. Like for every naming reaction, the point number one, what is reagent? Okay, the first question, what is reagent? The second question, what is the substrate? Or let me just write the reactant. Reactant, or you can say the substrate. Or the third one is what product. Okay, so for once the let's suppose this naming relation come in your paper, okay, in future maybe. So how to call this reagent, reactant, product, substrate, everything you have to know. So let's start with this. That is what is Kolbe's reaction, which kind of reagent we are going to use for this one. Okay, so I guess I already have the slide. Let me just check reagent, reagent, reagent. So look at this. So what is the reagent we are using in this case? NaOH. So basically you are starting with some phenol, and at the end we are getting some salicylic acid. Okay, we are getting a salicylic acid. Don't worry, I will explain. Okay, just try to understand what I want to explain simply here. So in this case, first of all, you are having some phenol. Okay, this is some phenol there. Then we are using some reagent. So what are the reagent? NaOH plus CO2 and then H positive. Okay, so there's a like everything has a point. It's not like we're just using. So first of all, like in this case, we are using two reagent. One is the NaOH, NaOH. We will discuss about this point. Why I'm using NaOH here. Okay, why not the reaction directly go with the second reactant? So look at this NaOH, the first thing, and the second one we are using here, that is a CO2. Sometime maybe you're observing HCl, or sometime it is written only H positive. It means in a presence of acid. H positive, HCl, CO2, these are the things we are getting. And in this case, again, there is a two chances, right? Like we discussed this thing already two time. Look at this, it's a plus M. Okay, so definitely in this case, we are getting ortho and peri product. Okay, but most of the time in this reaction, we are just observing this is some phenol, and the product is what? This is the OH, and this is a COH is there. Okay, so what is the name for this one? It's a Celi. Okay, common name. It's really, really, really very important common name. Sometimes, everything is mentioned phenol, NaOH, and this. What is the product name? So it's a cyclic acid. Okay, salicylic acid or salicylic acid, anything you can use. Okay, this is the kolbes electrolysis. You have to start with phenol, and you have to use NaOH plus CO2, then HCl, then H positive ion, or then we're getting salicylic acid. This is the name of the reaction. But my question to you, why not this is also the product? Or why not the reaction is famous for this? What is so special about this salicylic acid? Or like if you have to go with the naming, like the naming starting from 1 2, so it's become 2 hydroxy. It become 2 hydroxy benzoic acid. No, this is the IUPAC name for this one. 2 hydroxy benzoic acid. So this is the product. Most of the time we are going to discuss. Then why not this? Please answer the question. Yeah, you're right. You're from my bench as well. I don't know about you then. Okay, so here I'm not explaining the single reaction. Okay, Sidhu, we are just finishing the syllabus only. Okay, everything in a very detail. Okay, okay. I am sorry. Yeah, I'm sorry. I'm sorry. I'm sorry. Okay, spelling mistake. Now it's okay. I'm sorry, Shiva. Yes, please answer the question. Okay, Shrivardhan. I know the Shrivardhan. No, I really miss you during my classes because you're a very good student actually. Yes, please. Not an issue. Yes, please. Why not the question mark one? First, make this point very clear, right? Come on. Why only salicylic acid, or why not this that para one? Yeah, same hydrogen bonding. Again, we are going to get this is a major product, right? Why? Because again, the same thing we are going to end up here. So let me just erase this. Actually, what is going to happen, okay? So in this case, again, we are getting a hydrogen bonding simply, okay? Like this is how the hydrogen bonding is there. Okay, cool then. So it's a major one, okay? Both is going to form, but still we are going to follow the major product. So major and minor is there. Point number one. The second point, that why NUH. So in just to understand the reason, let's just try to understand the mechanism. Mechanism not important for your board exam, okay, but it's really important for understanding this reaction. For just to understand this, okay, just try to analyze the thing how the reaction is going to follow, and then you are able to answer why I'm using NUH. Okay, so the mechanism, how about the mechanism for this reaction? Let me just first explain the mechanism, then I will told you the step as well. Okay, wait for this. So first of all, it's a phenol, the step number one. The step number one, in this phenol, we are adding NaOH. I hope you know very well what is happening now. That this is NaOH, the water is going to evolve. If I'm using this kind of sign, we noted it's be like water is living. Okay, why? Because you can say this H positive or this OH, both combined, and we end up with the water simply. Okay. Okay, so we are getting this Na positive, O negative. So what is it? It's a phenoxide ion. Or sodium phenoxide you can say as well. But I hope you already know this is just being like a counter ion. This is just being like a counter ion only, okay? Wait. Just in order to stabilize the charge. Yes. Then what is the use, okay? First, this is the point. And in a step number two. Okay, first answer the question. Why we are using NaOH here? There is any use of NaOH? Yes, I know, Sidhu. Yes, you're right, Shiva. Just wait. I will tell you every point one by one, okay? Wait. If you're using KOH, then we are end up with the para-azimuthal product. Okay? Shiva, you are right. You are right. Anisekitin, then what is the use of that anisekitin? I don't know, Batula, like what do you want to ask? Just try to understand my part. I will explain one more time. That look at this. Oh, sorry. If this is OH and this is a ortho position, so it's a COH group. Let's count the number. Start with this one, 2, 3, 4, 5, and 6. Okay, maybe you already know six member ring is really very stable. So whenever there is a formation of six member ring like this, okay, it's a six member ring formation there in this hydrogen bonding. So it's a one of the stable kind of intramolecular hydrogen bonding. So what is it? This is a intra inside the molecule. It's an intramolecular hydrogen bonding like the nitrophenol. Okay, intramolecular hydrogen bonding like the phenol. Sorry, orthonitrophenol. Let me just write here very small size, just try to understand. Again, recall that we just discussed orthonitrophenol one. Let's see the numbering again. Maybe you never notice about this, but it's very good point. Let's see the number of atom there. One, two, three, four. Wait. One, two, three, four, 5 and 6. So yes, do you know sometime how the question frame that in this case intermolecular hydrogen bonding there or not. So always count the six member ring again. Okay, so six member ring intra type of hydrogen bonding is really stable. Okay, I hope it's clear now, Batula, that why this is the case. Okay, not an issue. Sure then, okay. Yes, please. Is this point clear now? Okay, not an issue. Okay, let's continue. Okay, so that's it. Let's just back what we're discussing this. Okay, so be noted this O negative is just like a counter ion. So really what is happening? This O negative attack here and this bond open up like that. Okay, so what we are getting in this case now that look at this. Simple, it's a O negative. Okay, and there's a negative charge generated. Oh, sorry, double bond. An O negative charge generated in this case. And now we are using CO2, right? So for first question, CO2 is a acid or a base? CO2 is a acid or a base? Come on, answer this question. Acid. Okay, next question. Acid is a acceptor or a donor? Acid, yes. Okay, yes, acid, acid, acid. So you can say CO2 is a acid or CO2 is a normally we can say it's a very good acceptor now because Lewis acid is a very good acceptor. Okay, now the answer for this question, like why we are using NaOH here? What is the use of this N extra NaOH here? So be noted, the use of this extra NaOH is what? If let's suppose I'm using only phenol, okay? And the second condition is what? We are using phenoxide ion and CO2 is a acceptor. So from which this is it easy for a CO2 to accept the ion? Like A or B? Phenoxide is feasible or like phenol is feasible? Think about it. CO2 is a acceptor is a common thing, but between A and B, which one is a very good donor for the CO2? Yes, please. Which one is a very good donor, A or B? Mm, come on, I guess your juice is very weak, okay? I'm just feeling this. Okay, look at this. In this case, the condition number one, oxygen has a lone pair and hydrogen. Condition number two, oxygen negative charge plus lone pair. Did you notice something? That is the lone pair is the common point here. Okay, it is going to like donate like this. But which one is like a plus factor here? Negative charge. Negative charge species of good donor over the lone pair one. So it increasing the electron density more on oxygen and more on the benzene there. So directly indirectly, by using the NaOH, we are increasing the electron density on a benzene ring. Okay, means that phenoxide ion is a better donor. Better, you can say that what is the case here? That is a better nucleophile. So it's behaving like a nucleophile only. Let me just back again with the video. Yeah, this slide. So that's why we're using NaOH only. That's the only main mode of using NaOH. Otherwise, not any important use. So this is the point number one. That is a simple and which combine. So from there to there, it's a step number one, typical step number one, formation of phenoxide ion. Okay, now the step number two start. This is a step number two. It's a step number one. It's a step number two. What is the step number two? Attack of the benzene ring on the CO2 molecule there. Okay, so let me just explain this step on the next slide. Okay, it's a negative. Okay, it's a CO2. So negative attack here. This bond open up, and what we're getting. Okay, again, the third step is what? Again, deprotonation. Why the deprotonation? Of course, this is not benzene. Benzene wants its stability back again. So what is happening in this case? This is a hydrogen, or okay, this hydrogen simply attack here, and this bond open up. Okay, and this O negative going to abstract this hydrogen. I'm repeating one more time. Okay, this OH attack, this hydrogen attack here, this bond open up, and this OH, this O negative attack on this hydrogen. Okay, so what we're getting, this step is the deprotonation, typically the step number three. Step number three is what? Deprotonation, removal of proton, you can say. Okay, so what we're getting now, we are ready with the COH there. Okay, now look at this. In this case, the last step we are using acid, H positive, HCl. You can use H positive or HCl, anything. Any acid can be there. Any protic acid you can use. So what is the use of this H positive? Which will be like, okay, come here. So what we are getting that the thing which we really want, that is the salicylic acid. Okay, so let me just quickly brief you the mechanism. First of all, phenoxide ion formation, then attack on a CO2 molecule, and then this is the final product. Okay, this is all for the mechanism. Let's see the statement wise how it does look like. So observe this, that formation of phenoxide ion and then attack of the electrophile, because as we already discussed here, that in this case, wait, where's the slide? Okay, yes, look at this. If you're observing here, this is being like a nucleophile. It's a nucleophile part and it's a electrophile part. So basically, the nucleophile attacking on electrophile. Okay, so it's a step number two. And a step number three, that is a protonation. Like protonation means that like the last hydrogen is going to accept the proton one more time. All the like deprotonation is the good point here. But I guess you are getting my point. This is all for the which reaction? Kolbes reaction. Now there's a knot for you. What is the knot? If we are using KOH as a base, so we are getting, as we already discussed, ortho is the meso product. But if we are using NaOH, sorry, NaOH. But if we are using KOH as a base, so we are getting para product as a measure one. So answer is very simple because the size of the potassium is maximum of the sodium. So that's why the issue with the meta product there. Okay, it's not like final product. In between, let me just back again. If you know, let me just connect again the sodium there. So actually this is how it's look like. So sod, if you're using potassium here, so potassium has an issue with the size. So that's why with potassium, this position is not visible. You can say less chelation is there. Okay. Although I don't want to explain, but still, I'm going to explain. Listen my point. What is the meaning? What I want to explain to you here. Look at this. Okay. Maybe you already know that is a chelation or chelation. Anyone. What is chelation or chelation? That ligand connected and there's a kind of cyclic structure formation take place, right? For coordination chemistry. Okay. So in this case, this is a O negative and then sodium positive and then CH is there. Okay, so you can say that okay, there's a hydrogen bonding between them, but still the sodium form a kind of chelate between these two things. Okay, like it's a cyclic product, cyclic kind of thing. Wait to benzene. And this chelation is only possible for small size. Small size. So, like as we discussed in between, this is also the step here. So, but on the other hand, if you're using potassium, so potassium, like I can't go with this because my size is large. So, just in order to stabilize this, potassium prefer the para position is the major one. Okay, reason is very simple. Chelation is the reason because sodium has a small size, potassium has a large size. But again, if you are not getting ma'am how chelation anything, it is not the part of the syllabus. Just be noted. Sodium if you are using ortho product, if potassium you're using para product. Okay, this is all for the like explanation. This is all for the Kolb's electrolysis and this is all for the today's class as well. Okay, now your turn. Any problem, any point not clear, feel free to ask, please. I know maybe now organic chemistry become little bit complex, right? But just don't worry about this. Focus, revise the thing only and solve the PYQ. This is the only way so that you can master in organic chemistry. Okay, this is all from my side. So yes, any problem, any issue, anything you want to discuss, please ask. Am I not audible? Okay. 60% of the paper containing organic chemistry. Okay, Batula. So You are having a choice. You can drop the inorganic, but no, you can't drop the organic. The complete advanced only cover the organic portion or the physical. Inorganic weightage is very small, so you can't do this. Okay. Thank you so much, sir, and thank you so much, everyone. Thank you so much, Lakshmi. Okay, and have a nice day, everyone. Bye bye. Thank you so much. Thanks for joining the class. Let's meet again in the next class. Okay. Thank you so much, everyone.